So here's problem number 6. It's from the 2014 BC exam. And in this question, as normally happens in question 6, you're given some information about a series. So they say the Taylor series for a function f based at 1 is given by this, and it converges to f of x as long as the absolute value of x minus 1 is beneath r, and r is the radius of convergence of our series. And then what they ask us to do in part A is they ask us to find the value of r. So we want to know what the radius of convergence for this Taylor series is. Now anytime you're asked to find a radius of convergence or an interval of convergence, you're going to want to go with the ratio test. So here's the ratio test. And we're trying to figure out when this ratio is less than 1. And so we go ahead and figure out what the value of a sub n plus 1 is by putting n plus 1 in place of all of these n's. We also figure out what a sub n is and divide by that. You see I've multiplied by the reciprocal as you normally would do when applying the ratio test. You do see that I've omitted this piece right here. You don't see that anywhere within the absolute values here, and the reason why is because of the absolute values. This is always going to be 1 or negative 1. Well, when you're considering absolute values, 1 and negative 1 both have an absolute value of 1, so you can omit that. So when you start to try to simplify this a little bit, you have n plus 1 factors of 2 in this numerator, and you've got n factors of 2 in the denominator, so you can cancel that with almost all of the 2's in the numerator. You have one extra factor of 2 there. Similarly, if you look at this x minus 1 to the n plus 1, you've got n factors of x minus 1 sitting here. There's one extra factor of x minus 1 here than there is down here, so this is going to cancel with almost all of that. I can't cancel this n and this n. I violate the order of operations if I try to, since I'm reaching into this set of parentheses here. So it looks like my numerator is going to simplify to 2 times the quantity x minus 1 times n. Denominator is going to be n plus 1. Now within this limit, as n approaches infinity, this is essentially a constant. 2 and x minus 1 do not change as n approaches infinity. So I've factored those out. Now the absolute value of 2 is 2, so you see I don't have that in absolute values anymore. But I have to keep the x minus 1 in absolute values. I haven't specified what x is. That very well could be a negative difference sitting here, and so the absolute values would still have to be there to make sure that we affect that negative value in the proper way. And then you get n over n plus 1 left within the limit. If you use L'Hopital's rule on this, you're going to get a limit of 1 right here, and then 2 times the absolute value of x minus 1 times 1 just gives you 2 absolute value of x minus 1. You want to know when this is less than 1. That's when you converge. And so if you divide by 2, you get the absolute value of x minus 1 is less than 1/2. And then if you break this up, this absolute value inequality up into the two cases and solve each, what you end up with is you end up with an interval of convergence that goes from 1/2 up to 3/2. Our radius of convergence is half of that interval. So since the interval of convergence is 1 unit, our radius of convergence is 1/2. As we move into part B, we are asked to find the first 3 non-zero terms as well as the general term in the Taylor series for f prime. Well, if you have a Taylor series for f being given to you and you want to develop a Taylor series for f prime, the easiest thing to do is to just take the derivative of both sides of this equation. This is equal to f of x on the interval of convergence. And so if we do the derivative of both sides of this, on the left we get f prime of x. So on the right, this new series that we're writing out here will converge to f prime of x. Doing the derivative of this it could be a little overwhelming, but it's actually not that bad if you really think about what you have going on. You're not doing the derivative with respect to n, you're doing the derivative with respect to x. So this is a constant, so we can copy that into our new series. 2 to the n, as x changes, is a constant, so we can copy that into our series. Same thing with n. Now this piece right here, this piece that involves x, when we do the derivative of that with respect to x, we are going to have to be careful. We have an inner function x minus 1 raised to a power n that's not yet specified. So we'll multiply by that n, subtract 1 from it. We'll leave the inner function, the x minus 1, inside that set of parentheses. Technically, I should be finishing a chain rule here and multiplying by 1, the derivative of x minus 1, but that doesn't really affect anything, which is why I had it left off there initially. And then I just tried to clean this up a little bit. I noticed I had an n in this denominator, I had an n arise in the numerator, so those are going to cancel. And here is the general term in the Taylor series for f prime based at 1. You wanted the first 3 non-zero terms in that general term. So to find the first 3 non-zero terms, you're just going to take the first 3 values of our index, 1, 2, and 3. You're going to put those values here, here, and here, and then you're going to add together the results. So if you go ahead and do that and then simplify, what you end up with is this for the first 3 non-zero terms, and then the general term I just copied in at the end here. Last part of this question, kind of tough. Pretty lengthy as well. They tell us that the series that we just developed in part B, the Taylor series for f prime, is actually a geometric series. So what I have right here is I have a little bit about geometric series. We know the sum from k equals 0 to infinity of ar to the k is going to equal a over 1 minus r, or is going to converge to a over 1 minus r, as long as this base is in between -1 and 1. And so I'm going to have to try to make use of this because they tell us that this is a geometric series. And they were actually very nice in telling us that, because if you were asked to kind of determine this on your own, it would have probably taken quite a bit of time to realize this is something you could go to and utilize. So we're going to try to see if we can turn this into our geometric series definition. So what I noticed was that I have a whole bunch of different powers here, n plus 1, n, and n minus 1. And this is just the series that we developed back in part B. I know if I'm trying to use this Taylor series definition, or excuse me, this geometric series definition, what I'm going to have going on is a power that is the same, right? I want one power here. So what I noticed was, well, I can turn this into an n and then an n minus 1, and I can turn this into an n minus 1 pretty easily. Now, if I'm trying to turn this into an n minus 1, this term right here, this -1 to the n plus 1, I could write it as -1 times -1 times -1 to the n minus 1. Now, this is just going to be a positive 1. So basically, these cancel, and -1 to the n plus 1 is actually equivalent to -1 to the n minus 1. So, I thought about this little simplification process, but nothing really changes other than the appearance of the exponent to go from here to here. Now, if I want to change 2 to the n to 2 to the n minus 1, I'm going to have to peel off one of the factors of 2 represented here. So I'm going to have 2 to the first times 2 to the n minus 1. So this product is still equivalent to this, but now I have a power that matches the power that we just developed here and the power that we already had on this third piece of the product. Why is this beneficial? Well, now you can write this as a single base raised to the n minus 1 power. So I'm just going to take the -1, the 2, and the quantity x minus 1. I'm going to multiply those together, and I'm raising that collectively to the that product collectively to the n minus 1 power. I do have this extra factor of 2 that comes in right here. Now I'm going with this geometric series definition, and I want this power right here to not be an index -1. I want it to just be the index. So what I went ahead and did was I changed my index. I wanted a new index here. I'm calling my new index I, and I'm saying that I is going to be equal to n minus 1. So when I change this index, I don't affect this 2 at all. I don't affect this base. I do affect the power there. That was the main rationale for doing this. I get a power of I replacing the previous power of n minus 1, but that's also going to cause some adjustments to the place where the index starts and the place where the index finishes. This is the n value of 1. I is equal to n minus 1. Well, if we take this n value, 1, put it here, 1 minus 1 is 0. I is therefore going to have to start at 0. Infinity minus 1 is still just infinity, so the upper limit of integration doesn't really change. Excuse me, the upper limit of the sum doesn't really change. This is pretty nice because now what we've built is we've built a geometric series that fits this definition back here. And this geometric series is going to have to converge to a, which is the coefficient out here, over 1 minus r, which is this base that's raised to the power represented by the index. And if you simplify that a little bit, what you end up with is you end up with 2 over 2x minus 1. And that tells us that f prime of x is going to be 2 over 2x minus 1. Now this equality across this line right here only holds on the interval of convergence. Okay, so I'm being a little bit loose notationally there. This equality only holds on the interval of convergence, so f prime of x is going to equal this function. Well, if we look at what part C actually asked us to do, it said find the function f prime to which that series converges on the interval of convergence, and then use that to determine what f is. So now that we know f prime, we need to try and shift our attention to determining what f is. So we'll do that on a new screen. So here's f prime of x. We just determined that. We want to know f. So it's just going to be an antiderivative to go back to the original function. And the antiderivative of 2 over 2x minus 1 is actually going to require a little u substitution, let u equal what's in the denominator. That causes you to pick up this factor of 1/2, which is kind of nice because it's going to cancel with this 2 that's floating around in the numerator anyhow. You get natural log of the absolute value of u for the antiderivative with respect to u. When you back substitute, you're going to have 2x minus 1 going back in place of u. Don't forget about your plus c. Now the last little thing that we want to do here is we want to figure out what the value of c is. We can actually figure out what f of 1 is because it's really easy to take the series that we started with. They told us that f of x is going to this series is going to converge to the function f of x on the interval of convergence. So if we want to know what f of 1 is, all we have to do is we have to put 1 in place of x in the series. And if we put 1 in place of the x in the series, that's going to give us a bunch of zeros, right? So this base is 0 when x equals 1, and so that implies that f of 1 equals 0. And so if we put 0 in place of the y right here, and we put 1 in place of the x right here, and then proceed to try to solve for c, we did all that work just to see that c was 0. And that tells us that f of x is going to be the natural log of the absolute value of 2x minus 1. So part C especially, kind of tricky, kind of lengthy, but hopefully that provides a little bit of clarity.